Is there any doubt? How to find single source shortest path by using BellmanFord algorithm? Right? So today we'll see the algorithm of that. Then we'll proceed with another example. I hope my screen is visible. Right? Okay. Is my screen visible?
Yes, sir.
All right. You can just observe here
Yes, sir.
the simple steps we are writing for BellmanFord algorithm, where it is accepting the number of vertices and the distance, cost of the edge, and v, right? So we should find a single source shortest path with negative edges. We should find single source shortest path with negative edge cost. That is what the advantage of BellmanFord algorithm, which we studied in the previous class, right? This trust algorithm cannot be applied if we are having negative edges. So hence we are going with the BellmanFord algorithm, right? So here we just observe here. First what we are doing from 1 to n. From 1 to n, we are initializing the distance of each vertex, right? We are initializing the distance. We just see distance of I is equals to cost of v to I. Okay, cost of v to I, right? Next. So we are considering the first vertex as a source vertex. Then we are going with the second vertex up to n minus 1, right? Up to n minus 1 we should find. So for each u such that u is not equals to v and u has at least one incoming edge, then what we are doing, just see for each I comma u in the graph. So we are doing if a distance of u is greater than distance of I plus cost of I comma u. So this yesterday we wrote like this: if distance of u plus cost of u comma v is less than distance of v, then distance of v is equals to distance of u plus cost of u comma v plus cost of u comma v, right? I hope this is what we followed in the previous class, right? You just observe here the same is here. Okay, so instead of v here, so here we are taking the edge as u comma v. Okay, in this case we are taking the edge as u comma v, whereas in this case so they are taking the edge as I comma u. Okay, the edge as I comma u, except that everything is same. Here we are checking less than d of v, and here it is checking greater than d of I plus cost of iu. Same, both are same, right? Okay, so don't confuse with this. So if we are, so here we are taking, yesterday we considered the edge as u comma v, and whereas in this algorithm it is considering it as I comma u, except that the logic is everything same. Okay, clear? We'll just observe here. So that is what we learned in the previous class. For relaxation operation, if d of u plus cost of u comma v is less than d of v, if this is true, then we are calculating d of v as d of u plus cost of u comma v, right? So that is how we have calculated. Okay, we have calculated, right? So this is the algorithm we are having. Okay, now next if suppose you observe that one, observe this. So a is there. Okay, so here b is there with 2, and here c is there, here d is there, right, with -1, and here let us take it has -2, and here it is 3. Okay, and here it is 2. You just observe here. You just observe here in this graph. In this graph, okay, in this graph, you kindly apply the relaxation operation. Kindly apply the relaxation operation. Okay, actually, for 3 cycles, for 3 cycles, it has to end. But you just observe here. So initially, the source vertex, let us take 0, infinity, infinity, infinity. Okay, first wedge. So a comma d, let us take 0 plus 2 is less than infinity. So 2 is updated here. Similarly here, 2 is updated. Similarly, next up, b to c, let us update. B to c, let us update. So 2 plus 3, 5. Next c to d, let us update. C to d, 5 minus 1, 4 is less than, no, it remains unchanged. Next d to b, 2 minus 2, 0. 2 minus 2, 0. Okay, first cycle is finished. Next, second cycle. Second cycle. Next, second cycle. A to D. So A to D, 0 plus 2 is less than 2. No. So leave as it is. 0 plus 2 is less than 0. No. Leave as it is. 0 plus 3. Yes, it will change. Next, 3 minus 1, 2. It will not change. Next, 2 minus 2, 0. Right? 2 minus 2, 2 minus 2, 0. Okay, so it will not change. Second cycle is finished. Next we will go for third cycle. So 0 plus 2, 2, 0 plus 2, 2, 0 is less than, okay, it will not change. 0 plus 3, okay, 0 plus 3, so 3, it will not change. 3 minus 1, 2, it will not change. 2 minus 2, 0, it will not change. So 3 cycles has been finished. But in third cycle, it is left as unchanged. Okay, it is working now. Next, the same graph you just observe here. A, okay, 2. So here B, here it is C, okay, here it is 1, and here it is -2. Okay, now you just observe here. Now you just observe. Initially it is 0, infinity, 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 right? So 0 plus 2, yes, it is changing. So here 0 plus 2, yes, it is changing. Okay, next time. So 2 plus 3, 5, right? 5 plus 1, 6. It is not changing. It is not changing. So 2 minus 2, 0. Okay, 2 minus 2, it is 0. Okay, one cycle is finished. Next, second cycle. 0 plus 2, 2. 0 plus 2, 0. Okay. 0 plus 3, 3. Right? So 3 plus 1, 4. 2 as it is. So 2 minus 2, 0. Second cycle finished. Okay. Second cycle finished. Next. Next. 0 plus 2, 2. Okay. 0 plus 2, 2. Here also 0 plus 2, 0 unchanged. Next 0 plus 3, 3 unchanged. So 3 plus 1, 4 unchanged. So 2 minus 2, 0. So for third cycle also it is unchanged. Just see for negative edge. For negative edge. For negative edge, it is working here. Similarly, here also for negative edge it is working. Right? Similarly, for negative edge it is working. Okay. Next example, let us take, right? Next example, let us take. Just observe here. So 1, 2, 3, 4, right? Okay. So here we are having 4. Here we are having 5. Here we are having 3. Here we are having minus 10. And here we are having 5. Okay. Now you just relax this one. Now you just relax. Now you just relax this. So if we are relaxing this one, so this is 0, this is infinity, this is infinity, and this is infinity. Okay. Right. So just apply relaxation for this. 0 plus 4. Yes. Here 0 plus 5. Right. Okay. Next, you just relax this. 4 plus 5. 4 plus 5. No. We will leave as it is. So here 5 plus 3. 5 plus 3. 8. 8 minus 10. 8 minus 10. It is 2. Right. 8 minus 10. It is minus 2. Yes or no? 8 minus 10. It is minus 2. So this is first cycle is finished. Next go for second cycle. Again 0 plus 4. 4 is less than minus 2. No. So leave as it is. 0 plus 5. No. Leave as it is. Next 5 plus 3. 8. Right. 5 plus 3. 8. So leave as it is. 8 minus. So can we apply this? Minus 2, 5. Minus 2 plus 5. 3. Right. 3. So 3 plus 3, 6. 6 minus 10. Minus 4. So second cycle is finished. Next, third cycle, let us go. 0 plus 5. 3 as it is. 0 plus 4. Minus 4 as it is. Minus 4 plus 5. Minus 4 plus 5. This is 1. 1 plus 3. 4. 4 minus 10. Minus 6. Right. So just see. So third cycle is finished. Next, fourth cycle. Again you observe here. Fourth cycle. What is happening? 0 plus 5, 1 as it is. 0 plus 4, here minus 6 we are having as it is. And here minus 6 plus 5. So here minus 6 plus 5. So we are getting minus 1. Minus 1 plus 3. So here we are getting 2. 2 minus 10. Minus 8 we are getting. See, in the fourth cycle also it is changing. In the fourth cycle also it is changing. But according to our convenience, according to our this BellmanFord theorem, what it says, you go up to number of vertices minus 1. So number of vertices are 4 minus 1. Only we should go up to third cycle and we should stop. But even after fourth cycle also, the distance is changing. Are you observing here? Right? Even after fourth cycle also, again the distance is changing, right? So this is the drawback of BellmanFord algorithm. Okay, this is the drawback of BellmanFord algorithm. That is what it says. The BellmanFord fails to solve if there are negative edge cycles. Okay, BellmanFord algorithm fails to solve if we are having any negative edge cycles. So hence it is required that the graph have no cycles of negative length. Kindly remember. Okay, no cycles of negative length. Is it clear? Kindly respond please. What is the drawback of BellmanFord algorithm? What is the drawback of BellmanFord algorithm? If a directed graph is having a negative length cycle, okay, a cycle with negative edge, then this BellmanFord algorithm will not be cannot be used to find the shortest path. Okay. Clear? Any doubt? Kindly respond, please. Any doubt? Kindly respond, please. Yes, kindly respond. So we cannot use BellmanFord. So it fails to solve if there are negative edge cycles. Hence, it is required that the graph should not have any negative length cycles. Right? What is the time complexity? What is the time complexity? Right? So it depends on number of edges and number of vertices minus one time we should do, right? So it is nothing but number of vertices and number of edges. So we are having n into n square, right? N into n square with respect to normal digraph. If the graph is complete graph, okay, if the graph is complete graph, then we are having n into n minus 1 by 2 edges. So hence we are having n into n minus 1 by 2 edges into n minus 1 number of vertices. So it is n cube. If the graph is complete graph, if the graph is complete, then the time complexity of BellmanFord algorithm is n cube. Else, if the graph is not a complete graph, then we are having n square. Clear? Kindly respond, please. Any doubt? If the graph is complete, then the time complexity is n cube. If the graph is not complete, then we are having n square. Okay? Any doubt? Any doubt? What is the drawback of BellmanFord algorithm? If a directed graph is having edge with a negative value, right, and it has a cycle, then we will call it as, then this BellmanFord algorithm cannot be solved. So that is a drawback of BellmanFord algorithm. The time complexity of this is, for not a complete graph, it is taking n square. That is number of edges into number of vertices, right? And so here, for complete graph, it is taking n cube. Okay, clear? Clear?
Yes, sir.
Okay, now you just try to solve this one. So here it is saying from node 1 to every other node. So solve this one. You try to solve this.